I'm Chris Staveley. I'm Chief Exec of Smart Fibres. I'm going to be talking to you about the work we've been doing with optical fibre sensing technology, particularly in the oil and gas industry, and how we've exploited it for production optimisation and condition monitoring of some subsea assets. So my agenda will firstly introduce the technology to you, and we'll go through 3 case studies in the oil and gas industry, and then I'll finish off with some look forward as to where this technology might be taking us in the future. Now, I've got quite a lot of slides to go through this afternoon, so it's going to be quite a sort of top-level look at the technology and the applications. Hopefully I won't be going too fast, but there might be a bit of time at the end for questions. If not, we're here for the next 2 days. We've got to stand out in the lobby and you can see some of the technology being demonstrated. So we're a small company, somewhat smaller than Hawaii, that's for sure. We've got one office here in the United Kingdom. We're established in 1998 and we're active primarily in the energy markets, oil and gas and renewable energy. We've also got some activity in some secondary markets as well. So our technology is based on the fibre Bragg grating. It's a fibre optic sensor. Bragg happens to be the name of the chap who discovered the technology some decades ago. And this slide shows you how the sensor works. And I think really the main thing to take from this slide that the sensor is a point sensor rather than a distributed sensor, and it's sensitive to 2 things. It's sensitive to strain and it's sensitive to temperature. And the way we turn the fibre into a sensor, we irradiate it with UV laser light, and it creates a wavelength selective mirror in the fibre. And as you can see from the top right graphic, the wavelength that's reflected from the sensor varies with tension and compression, so therefore you can use it as a strain gauge. And from the bottom right graphic you can see that the wavelength reflected also varies with temperature, so you can use it as a temperature sensor. Now, the important thing is these 2 effects are independent. So if you have control or knowledge of your temperature, you can use it as a temperature compensated strain gauge, or if you have no tension or compression on the fibre, then it's a very effective optical temperature sensor. Okay, so using that as our sensor, we can build up a fibre Bragg grating measurement system, and it comprises 3 components. The first component is a fibre itself with a number of sensors written into the fibre. They're point sensors, but we can have on one fibre, we can have many dozen sensors. We do that by making sure that each sensor has its own unique wavelength, and then we can demultiplex these sensors in the wavelength domain. So the sensors can be very close together. They can be on top of each other if you so wish, or they could be kilometres apart. The second part of the system is this guy up here. We call an interrogator. And what it does, it shines tunable laser light down the fibre, and then it measures the wavelength of the light reflected back from each sensor. It can then compare the wavelength reflected back with wavelength from a calibration that we do in the laboratory, and then over here, that wavelength data is converted into the measure end of interest and then used for whatever purpose the application needs it. Okay, so I've mentioned that the fibre Bragg grating is sensitive to strain and temperature. They're the intrinsic measure ends, but we can also develop transducers for measuring pressure by converting the pressure input into strain on the FPG. Similarly, we can do a load transducer, displacement transducer. We can do a transducer for measuring bending or curvature. We measure strain either side of a pipe or the root of a rotor blade, for instance, or a shaft. We can then, by subtracting the strains, we can get a bending moment or a measurement of curvature. There's also third parties that are working with fibre Bragg gratings to make acceleration transducers. We have some solutions for measuring flow with fibre Bragg grating. The first is a vortex flow meter that was developed by T&O in the Netherlands that we're bringing to market, and there's also opportunities for Venturi flow meters using differential pressure. Also, there are numerous other types of FPG transducers that are being developed by others, including and not limited to inclination, moisture, hydrogen, biological and chemical agents, electric current, magnetic field. And the important thing is that all of these sensors look to the instrumentation like a fibre Bragg grating. So you can have a multiplexed, multi-measure end system with one instrument. Okay, so why would you want to use this technology in the oil and gas industry? There are a few technology benefits when you compare optical sensing technology with its electrical equivalents. The ones that we've indicated in red here we think are of key relevance to the oil and gas industry. In the first instance is the ultra-harsh environment capability. Optical sensors are far more tolerant of extremes in temperature, also radiation and vibration, than their electrical equivalents, particularly because there's no downhole electronics. That's what gives you the increased temperature capability. Also, there are fewer components and no moving parts, so that increases other areas of robustness. Now, the second point is the multiplexing capability. As the last slide shows, you can have dozens of multi-parameter sensors connected on a single cable to a remote instrument, so it reduces the number of system connections and penetrations and what have you, which increases reliability and reduces cost. Remote monitoring is a key benefit, and we've heard already that fibre can transmit data over very long distances. And we can have the fibre on the top side or on the shore, and the instrumented structure can be up to 50 kilometres away without any need for amplification. And there are solutions for greater than 50 kilometre tiebacks as well that we're looking at. Obviously, zero power is a key benefit, particularly in the oil and gas industry where you need intrinsic safe operations. And also, if you're measuring a turbine or a motor, the fact that we're immune to EMI is important as well. The one that I skipped, long-term stability, there's no inherent measurement drift. We're measuring the wavelength, and there's absolutely no mechanism by which that wavelength reflected from the sensor will change over time. So we've got the potential to have a very stable long-term measurement, and if you're measuring, for instance, downhole pressure in a reservoir, that's really quite important. There's a couple of other benefits that are more related to the other markets. Okay, so the first case study is the development of downhole pressure and temperature monitoring system. This is a project that's been sponsored by Shell in Rijswijk in the Netherlands for some time, and the partner where we did the installation was PDO in Oman. And here the objective is to develop and deploy a low-cost optical gauge monitoring system, so sufficiently low cost that it becomes a value proposition to put more than one gauge in the well, so maybe 5 or 10 or even more than that. So the business case, I think there's a pretty clear business case in the industry now for the need for multi-point downhole pressure and temperature monitoring. It helps with production optimization, reservoir management, verifying your models, and monitoring the health of your downhole pumps. Add to that the system advantages of using FPGs. You've got no downhole electronics, which gives you a higher operating temperature. You've got the capability of dense multiplexing on a single cable, which means it's easier to run multiple gauges in hull. That adds to an increase in reliability and a reduction of cost. So this is a product that we developed under this 5-year project with support and steer and some sponsoring from Shell. The gauge is a fibre Bragg grating pressure transducer. We have one fibre Bragg grating here on the back of a pressure-sensitive diaphragm. So when hydrostatic pressure is applied to the diaphragm here, the diaphragm deforms. The fibre that's attached to the back goes into extension, the wavelength increases, therefore we can measure the pressure with one fibre. The other fibre is used to measure the thermal expansion of a coupon here, which is not subject to the pressure, and that gives us a temperature compensation device. This is an image of the gauge that we put down hole. There's a 1/4-inch control line coming in and coming out, and the fibres run through the 1/4-inch control line. So the fibre itself never sees the wellbore fluids. So under this project, we qualified the technology for obviously its pressure response to inputs, and we did that with deadweight test facilities. We tested the temperature response in thermal chambers and water baths. We did some accelerated testing, temperature accelerated testing to verify the long-term stability, and we obviously did shock and vibration testing as well. And then before we went to the field, we wanted to do a trial deployment. We did this in 2008 on a 200-ton drilling rig that Shell commissioned in their Rijswijk headquarters. And we were very pleased to be the first technology that was tested out on that rig. So we did a trial run-in hole of 5 gauges to demonstrate that they would run in hole nicely. And this is how the gauges are run in hole. In the first installation, we were measuring annulus pressure. So we literally clamped the gauges to the outside of the tubing string using a slightly modified cannon clamp. So this is a pressed steel cross-coupling protector. So a very low-cost way of putting the gauges in hole. So the well we selected for the field trial was with PDO in the southern field in Oman. It's a natty field. That's a thin ore ring reservoir. It's a fractured reservoir, and it's produced by gas oil gravity drainage. And the challenge that they have there is controlling and knowing the thickness and position of the oil rim. So we felt that with multiple pressure measurements, we can measure the pressure in the water, the oil and the gas, and then extrapolate the pressure gradients to then calculate the interface levels. So that was the challenge that we set ourselves. A couple of pictures of the well. It's a very average well that you would expect to see in the desert, and standard workover rig where we run it in whole. We run it in whole over a period of a few days, so we had a day shift and a night shift as well. So here is a sensor being connected to the tubing string. I think here they're running the cable through a packer. And then the cable is passed through the Christmas tree at the wellhead, and we have a pressure barrier to make sure there's no opportunity for any gas or wellbore fluids coming up through the cable. And then the cable is terminated at a surface instrument. So inside here is that interrogator, which was the blue box in a few slides back. And then there's a solar panel, and then we've got a remote transfer unit that beams it off to the local flow station, and then it's on the PDO network, and they have access to it via the Shell Pi database. So the result of this case study was during 2009, we installed 9 of these PT gauges, deployed them successfully. Data from 6 of them were used to chart the progress of the oil rim over 9 months during 2009. So the red band is the oil rim here, the orange band is the uncertainty of that measurement. The current status is we went through an upgrade of the system design to improve the reliability, so that next time when we put 9 in the hole, 9 will work. And also we're planning a redeployment to prove the new system, and then planning a volume rollout in Oman and in other territories later on in the year. And we've also got some production monitoring trials planned where we're measuring the tubing pressure rather than the annulus pressure to get an indication of flow allocation in production. So the second case study uses the same technology, but it's a very different application. Here we're now looking at the development of a condition monitoring system for a subsea pump and motor. Sponsored again by Shell, but this time it was Shell Upstream Americas in Houston. And the objective here is to have us develop and demonstrate the capability of fibre optic condition monitoring in ultra-deep water environments, and particularly for rotating equipment. So here the business case, again, is fairly clear for the need for condition monitoring in subsea equipment. There's a real desire to get an early detection of damage such that you can have a planned exchange of the pump motor module or the Christmas tree or whatever asset you're monitoring. And it really does minimise the production loss due to downtime. But one of the key value propositions is the reduction of the cost of the mobilisation of the intervention vessel. So a big pump and a motor on a skid could weigh up to 40 tonnes, and there aren't many ships that are available to lift these out of the water and put them back in. Somebody in Shell told me that you can pay up to $900,000 a day to charter one of these vessels. So if you know you're going to need one when it's in your waters, it's a lot cheaper to use it then than to wait until your pump fails and then call it and pay for the 5 days journey for it to come to you. So the value proposition is clear. Add to that the FPG system advantages. We've got no subsea electronics, which increases reliability. We've got all optical gauges, which are suitable for ultra-harsh environments. And we can measure many different things on one cable. So again, we've got fewer connections, which increases system reliability. So here's that concept in graphical form. Up on the FPSO or maybe on the shore, you've got your instrumentation. So your electronics is here. Down here, all you've got is optical gauges. So there are no moving parts, all optical, no electronics, increased reliability. So here's the key thing, no subsea electronics. And the weak point in this system is the electronics. And in this architecture, if the electronics fails, well, you just unplug it and plug another unit in. So with that in mind, we developed a solution on a FlowServe 4 megawatt twin screw pump. This was an ultra-high boost twin screw pump that was being developed by FlowServe under a separate contract funded by Shell. And Shell asked us to develop a multi-parameter monitoring system, install it into this pump and the associated electric motor. And it's a pretty big pump. It's 4 megawatts. Its design rating is 4 megawatt. And the motor in particular has been proved to be able to deliver 6 megawatts. So it's a significant piece of kit. And what we did, we put some sensors inside the pump itself. We wanted to measure the strain and the acceleration on the main pump rotor bearings, which have been identified by Shell as being a potentially weak point in the system. We also measured the pressure and temperature of the lube oil in the pump. And in the motor, we wanted to measure distributed temperature through the windings so we could get a temperature map across the windings to see if there's any insulation breakdown, any hot spots. And we also measured acceleration around some of the bearings in the motor as well. So this is how we measured the temperature in the windings. We had a couple of tubes that ran into the windings, and we fed fibre into those tubes. They were PTFE tubes flooded with oil, so there was no air gaps, no dielectric effects to worry about. And of course, being all optical fibre, we had no susceptibility to electromagnetic interference. So with these two fibres, we had 9 fibre Bragg ratings on each of those fibres. And because they were loose in the tube, there was no strain on the fibre, so the only sensitivity we had was a sensitivity to temperature. Therefore, we were able to give an 18-point temperature map of that motor. On the pump, we wanted to measure the lube oil to make sure that it was being properly lubricated. This is fairly straightforward for us. We used a similar diaphragm pressure gauge technology that I showed that we developed for the downhole application. For this particular pump, it's rated up to 5 kpsi and 150 degrees C of lube oil, so we installed a sensor that was capable of those measurements. And here you can see again we have some stainless steel tubes, and the fibres again are inside the tubes here. So the fibres, apart from inside the pump, inside the motor temperature monitoring where you got flooded oil, the fibres inside the pump didn't see the lube oil. We also wanted to measure acceleration on the bearing housings, and there are FPG acceleration sensors. We don't develop them ourselves, but there are plenty of very competent third parties that do. So we package them inside a 1 atmosphere pressure vessel and put them on top of a bearing housing here, and we package them in a tri-axis arrangement so we could measure acceleration in 3 different directions. And the technology is able to measure from DC all the way up to about 1,000 hertz. This particular transducer has a first point of resonance of 3 kilohertz. So for these pumps and motors that rotate at maybe up to about 2,000 RPM, this is a suitable bandwidth to do our measurement within. The other thing that we wanted to measure that I think we got the best data from was the actual strain in the bearings themselves. I mentioned that Shell had already identified that the bearings were a potential weak spot in the system, and there are 4 of them. There's 2 at the drive end of the pump and 2 at the non-drive end. And this is a twin screw pump arrangement, so we've got a drive shaft that comes from the motor and a driven shaft. So these 4 bearings, we happen to monitor 2 of them in this application. And we did that by attaching fibres to the outer race of the bearing. This is an SKF bearing. It's called a carb bearing. It stands for compact alignment roller bearing. Very specific design for this type of application. Here you can see the construction of the carb bearing. It's got barrel-shaped toroidal rolling elements, and it particularly allows a lot of translation of the shaft with respect to the bearing, and can still provide the load transfer with that translation. So we worked together with some experts at SKF and decided where to put the sensors, and particularly we wanted to put the sensors in an arrangement that allowed us to measure not only the principal rotor load, which is a measurement that in practice the pump operators don't have, but we wanted to measure some other things as well. So we placed the sensors here at the main loaded point, but also either side of the main loaded point, and we did it on 2 separate rings, one on the left and one on the right hand side of the motor, of the bearing. So as well as measuring this principal load A, we could measure the tilt of the load from the vertical to see if there's any rotation of the bearing within its housing. We could measure the twist of the load from 12 o'clock, again to measure to see if there's any skidding or slippage of the bearing within its housing. And also by comparing the load on one side of the bearing to the other, we could see if there's any translation of the shaft compared to the initial location. And for Shell, that was very useful because it allows them to see if the twin screw loads are completely set up and the geometry that they set up in the twin screw pump was maintained. Because obviously with a twin screw pump, it relies on having 2 screws that are very close together but not touching. So if there's any change to that geometry, they really want to know about it as soon as possible. So looking at these loads, we had SKF calibrate the bearings for the load before we installed them, and then when we ran the pump we could compare the actual loads with the calibrated load and see if it compared well with the model, and there was pretty close correlation. So I don't know if you can see this, but here's a calculated load on the drive end bearings, calculated at 188 kilonewtons. We actually measured 184 kilonewtons, so pretty close. On the non-drive end, the load was calculated relatively lower, 126 kilonewtons, and we happened to measure 132 kilonewtons. So again, we're pretty close to the calculated loads. So that's what we did with the static data from the bearings. The dynamic data gave us even more insight. So one of those fibre brake gratings, each one of them we measured data at 10 kilohertz, and this is a typical trace that we get from one of them. And what you can see is the signature of each of the rolling elements passing. So there were 16 rolling elements, so between this peak here and this peak here, this is one rotation of the bearing. So the first thing you notice is that the load contribution differs from element to element, which is perhaps interesting. It can tell you if there's one particularly oversized or undersized. But also you can count the speed of rotation of the bearing cage and compare it with the speed of rotation of the shaft, which you get from the SCADA data of the pump. And if there's any difference in the two, you know you've got some slippage or some skidding, which is a very important thing to look out for. And this data is just completely one-to-one. Within the measurement resolution, it's a straight line at 45 degrees. So this verified that there's no bearing skidding. We also wanted to find another way of measuring the rotation without using electrical sensors. There's a little video embedded within this presentation. So here you can see how we did it. We, via this rapid prototype model, we attached a couple of magnets to the rotating part, and then we instrumented a non-rotating part which had some properties called magnostrictive. Now, magnostrictive means that you get a strain induced in this component here when it's in the presence of a magnetic field. So as you can see here, when each of the magnets pass, we get strain due to the magnetic field presence, and then we have strain peaks, and we can measure the leading edge of those strain peaks and then determine the rotation of the shaft and its speed. So again, as far as the system on the top side is concerned, this is just one other fibre brake grating. So you can plug in as many different measurements as you like. I think for me this is probably the most interesting slide in the presentation. This is some real data that we got from that 4 megawatt pump and motor. It's on a test stand in Etten-Leur in the Netherlands right now, which is one of Flowserve's big facilities. And this is enveloped data from one of the bearings, one which has got, well, it's got no damage. And here is another one of the bearings which we put in inverted quotes damage. And these are tiny strain signals. That's 5 microstrain. And the scale is the same on both plots. But you can see there's a big difference between this one here and this one here. And we determined the difference comes down to this rolling element here. Every time this one rolling element passed its respective sensors, we had a peculiar little glitch. Now, we at first thought there was something wrong with our measurement system. After some investigation and looking at the bearing data, we determined that there was an amount of damage on that particular rolling element. It has a coating on it to stop it wearing, and it was detected that that coating was beginning to flake off. Now this coating is only a few microns thick, so what this chart shows me is that you're able to see damage of micron level from the top side, maybe some 50 kilometres away from where that damage is being initiated. So it's a huge insight now into the state of condition of your machine that the operators simply didn't have before. I mean, this is obviously a lot of information, and the danger is having information overload. So that's a completely different matter, subject matter about how you take all of that information and process it into something useful. But we've certainly got a system that's sensitive enough to give you that information. So the result of this project is that we developed a multi-parameter system measuring numerous things with fibre brake gratings, and it was demonstrated on this machine here. So here's the pump module, here's the electric motor, here's a subsea wetmate fibre optic connector, which is how we connect the system. These happen to be subsea wetmate power connectors. Current status is that together with SKF, who are the bearing experts, we're maturing the instrumentation, maturing our knowledge of what the data that coming from the instrumentation is telling us. At the same time, Shell are seeking partners for the next stage of the funding of the main pump. And when that moves forward, then we'll move forward with instrumenting the next stage. Okay, the third case study, again very different, but again using the same technology, using fibre brake gratings. So here the application is to do fatigue monitoring and wire break detection on a flexible riser structure. So here the sponsor is NKT Flexibles in Denmark, one of the major riser manufacturers, flexible riser manufacturers. And The objective here is to improve the riser integrity management with embedded fibres. Now, there were two systems being used alongside each other. So the strain monitoring and the tensile armour wires, that's using fibre brag gratings from ourselves, and at the same time our friends at Tendeka, who have a distributed temperature sensing technology, were looking at monitoring of the annulus temperature. So the business case again is lowering risk through condition monitoring, and this is a business case as seen by NKT. So the way they see it, by looking at the structural and temperature issues and addressing them earlier, they can improve their decision making, allow themselves to compare the actual performance of the structure compared to its design, and it all adds up to an ability to increase the period of time in which you can safely operate your structure at its optimum level. So there's the business case for the monitoring, and here you've got the specific system advantages of going fibre. Again, we've got no subsea electronics. We've got an ability to fully embed the fibre within the structure, so you're measuring right at the point of the signal. So again, with the bearings, that data that we picked up from those bearings was only possible to see because we were measuring the data right at the point where the signal was originating. If we had put well, actually we did. We put an accelerometer on the bearing housing and we didn't see that fault. And again here, we're measuring things going on right inside the structure. So if we put measurement on the outside of the structure, the things that we can see, we wouldn't have been able to see. Particularly with the DTS as well, a key fibre optic advantage is that you can monitor all the way along the length of the riser. Okay, so I've got some very nice pictures here that the guys at NKT have put together, and this shows you what the system looks like. So these are the tensile armour wires. They wrap in a helix pattern around the structure, and they give it its main strength. Now, I was surprised to hear that in normal operation you can maybe have a dozen different breaks of these tensile armour wires, and it's still appropriate to keep using that pipe. But they want to know how many wires are breaking and the frequency of the break, so they know when to exchange the... They usually exchange the top section because the top section is where all the loads are, and if they have an instrumented top section, then they're able to exchange that without exchanging the whole riser pipe. And so NKT developed the technology for putting the fibres inside the structure. We can't claim any benefit for that. They did that themselves. They've also developed a very robust end fitting. On the DTS side, the application here is to monitor the temperature in the annulus all the way along the length of the fibre. This is to detect if there's any breach in the outer sheath, because when there's a breach in the outer sheath, obviously seawater will go into the outer sheath, and then these tensile armour wires are surrounded by seawater, and therefore they will start to fail. And this is the temperature trace. So under normal conditions, you've got high temperature in the coil because you're producing hot product, and then you've got a pretty quick drop of temperature. But if you've got an outer sheath breach, sorry, the red one is a normal case. If you've got an outer sheath breach, then the seawater temperature comes all the way to the inner pipe. So by looking at this temperature profile across the whole structure, NKT can determine if there's a breach, and if there is, then they can send down an ROV to have a closer look, and then they can make a repair. So at the same time as the DTS system being developed by Tendeka, we were developing a system for the wire strain monitoring. Now, we can actually listen to a wire break because we can measure at 10, 20, even 50 kilohertz. So using the same sort of capability that I've just demonstrated on the bearing, we can look at very fast transient changes in strain, and using the processing that NKT have developed, we can tell if that's a wire break or some other effect going on in the structure. So the two areas where NKT wanted to put this measurement was right at the end fitting and also on the bend stiffener. So these are the two areas in their structure where they see the highest strains and the highest potential fatigue damage. So the status of this project is NKT have carried out a lot of work to develop the way of putting the fibres inside the structure. So here is one of the tensile armour wires, and they call it a wire, and it looks like a bar to me. It's a pretty heavy piece of kit, and here's an optical fibre embedded into the side of it. So this fibre is already in the pipe when we come along. NKT have carried out a lot of full-scale tests to determine the type of processing they need to not have any false positives. They want to know that what they're measuring is a wire break and not something else. So they've done all of that background work. Meanwhile, Smart Fibres have been working on developing customisation of our instrumentation to work for this particular application. and Tendeca have been working on their DTS system to suit the application, and also some data processing and visualization software. We would expect probably 2 years before we see one of these instrumented systems in service, perhaps next year. It depends on how NKT get on with their major client. So my last few slides is looking forward about what this technology might hold for downhole and subsea optical infrastructures for production optimization and for condition monitoring. So operators and service providers have been using optical sensors for quite some time now for downhole production optimization. And the subsea operators are starting to look at the same technology and they see the benefits of the technology for asset condition monitoring. So companies like ourselves and others are developing transducers of all sorts of different measurands that all can be measured by the same system. And the technology is maturing through the work of ourselves and others. And at the same time, there are industry bodies looking at standardization for the use of the technology, particularly in the subsea field where standardization is very important. So looking ahead, one can imagine a complete optical infrastructure on the seabed and downhole where, if correctly applied, it can give the operators a possibility of improving total recovery, reducing their operation and maintenance costs, improving the safety and reducing environmental risks. Thanks, that's the end of my presentation. So we've got some time for questions.